Okay, hi, I'm Julien. I'm one of Alice's PhD students here at Berkeley, and I'm here to talk to you about the Berkeley black carbon sensor. We're still working on the name, but it's a small sensor that's unique in its ability to measure black carbon, an important pollutant, in a very versatile and inexpensive way. So there's currently 3 billion people, roughly half the world's population, that rely on cook stoves that burn wood, charcoal, and other biomass. These stoves are often nothing more than just 3 rocks with a pot on top. They're really inefficient, and they produce a ton of particulate matter, which when people breathe it in, it's really harmful to their respiratory health. In fact, particulate matter from these sources is the greatest environmental health risk in the world, killing about 4 million people a year, which is more than HIV, malaria, and a few other diseases combined. A really important component of particulate matter is black carbon, which we more commonly know as soot. These pictures, they're really pixelated here, but they're pictures of stalactites of literally like black carbon on people's ceilings and on their walls, collecting from using these cook stoves every day. And in addition to being really bad for people, but when they're breathing this stuff inside their homes, black carbon is the second largest contributor to climate change after CO2. And in these developing regions, the majority of black carbon can be directly attributed to these residential sources. So the overarching goal of our project is to measure black carbon so we can track where and how biomass is being burned. And eventually we want to use that information to better understand the impacts of these biomass cook stoves on human health, the climate, and the environment. The problem is that current technologies such as satellites or field campaigns of scientists going out in the field, they're really expensive, cumbersome, unreliable at measuring black carbon on the geographical and temporal scale that we need to make meaningful results, to have meaningful insights into this. The state of the art right now are instruments known as ethylometers. These are 2 of them. They're usually large laboratory units that sit on a bench like this, and even the smaller handheld one, this is the smallest one, they're usually all big lab instruments. They cost several thousands of dollars. So when you try to have a study with even 100 of these sensors, the cost becomes prohibitive very quickly. So there's a real need out there for a low-cost, compact sensor that we can deploy in large distributed networks to measure black carbon both on the ground, where it's generated and it's impacting people's health, and in the air, where it's being transported and it eventually affects the climate and the environment. So with that in mind, over the last year, we've been working to develop this little sensor. This is the 3rd prototype we have. We're working on a 4th. And first thing you notice is that it's really small, and it's made out of aluminum, so it's really lightweight as well. This makes it really easy to stick it into another instrument package. More importantly, it's really inexpensive. So the materials used to make this little sensing cell, it's less than $200. I should point out here, to be completely fair, that this alone doesn't output a black carbon measurement. You need a battery, a pump, a few other things, but this is the brains of the machine, and the vast majority of the cost is usually tied into this little sensing cell. So the way our instrument works is the same as all particle photometers, which is you have a filter, and on one side you have a light bulb essentially, and on the other side you have a light detector. And as you pass air through this filter, black particles, the black carbon, absorb some of the light passing through. So the light passing through is attenuated. We can then relate that reduction in light reaching the detector to the amount of black carbon in the flow. One unique feature of our instrument is that after it's passed through this signal filter where the black carbon's collected and the air is now clean because it's been filtered, it also passes through a reference. And what that allows is to cancel out for effects from relative humidity, temperature, other changes in the atmospheric conditions that would lead to wrong readings or changes in readings that aren't a result of black carbon. And I'll go into that a little bit later and show you the effects of that design feature. So we've been testing this in the laboratory so far at Dr. Kerstetter's aerosol emissions lab. And what we have up there is essentially a giant Bunsen burner that's upside down. And it produces very stable black carbon emissions that we then measure both with a commercial instrument and with our sensor. We compare the two results, and we basically see where we're at. We try to get them to line up. This is some of our latest laboratory trial results. So on the y-axis here is black carbon in micrograms of the particulate per meter cubed of air that it's sitting in. The red line represents a commercial instrument that we were testing against. In this case, it's the McGee, the large blue benchtop one I showed you earlier. And the blue line rather, represents our sensor. So we've done dozens and dozens of these trials, and we've been able to show that our little sensor provides accurate black carbon measurements when compared to its larger, more expensive cousins. But it does so in a uniquely economical and lightweight package. So one major failing of, or not a failing, but a weakness of all ethylometers, the traditional types, is that they're very sensitive to relative humidity. So this means that if you take a normal ethylometer, like that little blue one, and put it in a balloon, for example, because you want to do vertical profiling, that balloon passes through a cloud, and the relative humidity changes by 10%, whatever it is. That instrument will start giving you wrong measurements. It'll start giving you negative numbers. There's no such thing as negative black carbon. It'll give you huge numbers. So we can't trust it in those types of environments to give us accurate results. So one of the major design aspects we were focusing on is to completely eliminate this sensitivity. And the way we did that, the three-tiered approach, first, we use that dual flow pass I illustrated earlier. We pass air both through a reference and a signal, and we can cancel out the effect. We also maximize face velocity, so the velocity passing through the filter, we make that really fast so that any changes happen quickly on the filter, and then it goes back to equilibrium. And then finally, we use Teflon filters, which the same way they keep food from sticking to your pan, they keep water from sticking to our filter. And that also reduces the sensitivity of the instrument. So this plot up here shows the result of those three things in action. What we did is we set up 3 instruments, 2 commercial instruments, and our sensor with a flow of air that had no black carbon in it. All we were changing is the relative humidity of the air. So technically, if all the instruments are working as advertised, they should all be reading 0 the whole time because there's no black carbon in there. The purple line represents the change in relative humidity on this y-axis here. So you can see we gave it nice, neat steps of relative humidity over the trial. And what you end up seeing is that the commercial instruments in green and blue, every time there's a change, and particularly changes that are larger towards the middle here, there's a large spike of fake black carbon, essentially. It's not really black carbon. It's just a measurement artifact. And what you see is with the red line, our sensor here, we don't get this effect. You still get little spikes, which is good. It shows that our instrument isn't doing nothing. It's not just not responding to anything, but we've reduced the effect by an order of magnitude or so. And eventually what this means is that we can stick our instrument in balloons, in long-term ground monitoring station, and anything you throw at it, it should give you an accurate black carbon measurement, which wasn't possible with the other instruments we were trying this with. So now that we've been building this sensor in the lab, it's important to measure emissions not from a Bunsen burner, but where it matters in the atmosphere. So one of the people I'm working with on this, Daniel Wilson, he's a PhD student here as well. He did his Fulbright out in India at IIT Kanpur, and he worked on designing a balloon platform which would send data from a weather balloon that's rising through the atmosphere back down to the ground. And this is him with his team at the airfield where they're about to launch. And I'll show you guys a really quick little video of that launch. So this is the satellite modem. It sends everything to some sort of internet, and it shows up on Google, which is great. Like once we start doing larger deployments, we'll be able to just look at it in real time on literally a Google map. This is him with his team, really stoked to finally get this thing in the air. It launches. And you'll see as it rises over the city, you're going to see the smog that one day we'll be measuring. I didn't get to put a nano-S in this one. It wasn't ready at the point. But this is the city. And this is not all smog, but a significant portion of that haze is the black carbon we want to be measuring one day, and other particulate matter scattering. And that's the balloon at its apex, and it drops back down in a parachute, and they go get it. So this shows some of the data that was collected by the balloon. Here in real time, it gives you the location and its altitude. And like I said, it goes directly to the internet. So once we start launching 100 of these or whatever, we won't have to listen to some radio. It'll come right to your computer, and you'll see it. And this is some of the data. Even though there was no black carbon sensor on board, there was some other sensors like relative humidity, the temperature and stuff. And it shows that both on the rise and back down, we were able to collect data reliably in real time from this platform. So quick summary, we were able to build a tiny little black carbon sensor that compares very favorably with its larger cousins in the laboratory. We also built a platform so that we could deploy this to places where we want to measure emissions and get insights into that. And we'll hopefully, well not hopefully, we will combine these two pieces to enable better black carbon monitoring and eventually understand the biomass cook stoves that produce these emissions in the first place. Thank you.
Thank you, Julien. Do we have any questions for Julien about his sensor or black carbon? What other things we might have been inhaling over the last? Yes, sir, in the back.
I don't really understand what path does the black carbon take once it's been measured? How do you clear the filters?
That's a good question.
Let me just repeat that for the video. So the question was, how does the sensor clear out the black carbon once the carbon has collected on the sensor interface?
So after a certain point, once you've collected a certain amount of black carbon on the filter, you need to change it out. And there's different ways to go about that. If we're doing a balloon trial, our sensor is designed to just be lost and forgotten. We're not going to go get it. But the ground monitoring units we're working on will have, it'll look like a cassette essentially of filters, and it'll run through, little head lifts up, puts in a clean filter, and you move on.
So it's a cumulative measurement, not a time.
Yeah, it's a cumulative measurement. So you basically take the derivative of the light attenuation coming out the other end. So you see how fast the light is diminishing, and based on that, and knowing how much air you've got to the instrument, you can figure out black carbon on the back end. It's called Beer-Lambert's law.